Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our finite element analysis and design software, RFEM. The topic for today's webinar is concrete design per the ACI 318 in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Moritz Bertram will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. I always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So to quickly go over the content for the next hour today, I want to first explain RFEM and the add-on module concepts specific for concrete design, especially for those of you who are not familiar with our software. Then we'll move on to a concrete building example within RFEM. Here we'll take a look at the overview of the modeling and loading according to the ASCE 7 within the program. We'll run a full analysis. We'll take a look at our results and how to interpret these results so that we can take them into our own design tools, whether that's hand calcs, Microsoft Excel, or in-house tools to do the reinforcement design. Now, with that said, there are design add-on modules implemented within RFEM. And in particular, we'll be looking at today RF concrete members. Now, this will allow us to design our column and rib beams, as well as a wall spandrel above an opening within a wall with result beams according to the ACI 318. Then we'll move on to the RF concrete surfaces module. This will allow us to do design of our wall panels as well as deflection considerations with the module extension RF Concrete Deflect. We can also address singularities which may occur within finite element software and how this impacts our concrete design of 2D surfaces and what to exactly do about them. So to begin with, RFEM is our main program. This allows us to fully model, load the structure. We can create load combinations according to the ASCE 7, NBC standard, and run a full analysis. Now, with the analysis, we're going to get things like internal forces, deflections, and we can take those in, as I mentioned before, into our own tools, whether that's our in-house tools to do the reinforcement design. Now, in turn, we have our RF concrete modules within RFEM. This consists of two separate modules. The first is RF concrete surfaces. This allows us to run a strength and serviceability limit state design for 2D surfaces, whether that's elevated slabs or wall elements. And this includes design per the ACI, the CSA standard, as well as several other international standards. The second module is RF concrete members. This allows you to run, again, both strength and serviceability limit state design. We can include deflection analysis here for serviceability according to the ACI, CSA, international standards for 1D members, so beams and columns. Now, as I just mentioned, we do have the add-on module extension RF Concrete Deflect. So RF Concrete Surfaces is required in order to activate this module extension. This allows us to take a look at the analytical deflection analysis of 2D surfaces in the cracked or uncracked state with consideration to creep and shrinkage. And finally, we have the module extension RF Concrete Nonlinear. Now, this is applicable to both the surfaces and members module, and this allows us to run a nonlinear calculation for the serviceability state only in the crack state. So we won't be using analytical equations or factors, but we'll actually come up with the crack section properties and rerun this within the stiffness matrix to account for those nonlinearities. Now, we won't be getting into this today, but just keep that in mind that that is a possibility if you're looking for it. So we are ready to jump into our example today within RFEM. So for the sake of time, we won't be able to model the structure from scratch, but rather I went ahead and created this two-story concrete building. And you'll notice that we do have several surface elements. So the surface elements comprise our elevated slabs at both the first level and our roof level here. Now, those same 2D surfaces are also utilized for wall elements, and you can see these in the vertical direction here. Now, surfaces do allow you to apply any type of opening within them. So you can see that this might be some type of garage opening. We have openings for our doors, for our windows, and for our stairs. And this is all accounted for within the analysis. Now, you'll also see here these symbols, light blue here, that are located at the joints where our vertical walls intersect our elevated slabs. So what exactly are these? Well, this is what's called a line release. Now, a line release can be placed on any line element within the model, but in particular, we have added them in at this joint where the walls intersect the elevated slabs. The line release type, if we open up the detail settings here, has completely released the moment. So we will not have moment transfer at that joint. So you'll notice we also have translation here in the local X, Y, and Z. Keep in mind that these are the local axes of the line element itself. Then we just simply apply it to a particular line. We release the objects, and in this case, it's surface number 7, which is my vertical wall on the other side. So now we won't get any moment transfer between those walls to the slab elements. Under the display settings, we can scroll all the way up here to the top and we can turn those off. So they'll still be taken into effect within the background, but if it seems to get in our way when we're viewing this graphically, then we can go ahead and turn on and off elements like those within this display option. So moving on to the members, also within this display in our Project Navigator, I'm going to scroll all the way to the bottom. Here we can change the graphics, the colors in the graphics, according to some different elements. And the one I'm going to choose today is the member type. So the member types are 1D member elements within our software, but you'll notice that they are color-coded because they are different types of members. The first one to notice are our columns, and these are the member type beam. Well, a beam within RFEM is just any typical type of member, such as a normal beam or normal column. Nothing too fancy going on there. So that's why these typical columns just have the member type beam. Now, in turn, we have these pink colored members, and these refer to rib elements. Well, looking at a rib element, we can see here the member type is set to rib. We can expand the detail settings here, and what a rib allows us to do is to define the effective width on either side of the beam element with the slab modeled adjacent to it. So here we can set the effective width either as L/6, L/8, or we can manually type that in. So for this particular member, you'll notice that I do have a slab on the inside here hidden behind these dialog boxes. So I've set that effective width to 3 feet, just manually typing that in. Now on the other side, we do not have a slab available, so that's why this is set as 0. So rather than being a T-beam, it's more like an L-beam here. But we can fully consider the effective stiffness here for the slab element with the beam, and later on we can even design this rib type member in our RF Concrete members module. The last type of member that I want to point out is something that we call a result beam. Now, a result beam is very special in the sense that we're not actually modeling any type of beam member within this model when we're using a result beam. It adds absolutely no stiffness to the structure. But I have placed it above this wall opening, which we can see here, highlighted as the wall with the opening, and I placed this result beam right above it. Well, what a result beam does, if we double click on it and we take a look at the expanded settings, it will actually integrate the stresses and forces within a cuboid. So I've set this cuboid to 2 feet 1 inch in the vertical and horizontal direction. So now everything within that cuboid will be integrated and presented to me in a beam-like fashion. We can include only certain objects. So in this case, I only wanted to include my wall, surface number 9. So therefore, I'll get all of the internal forces, stresses, deflections above that wall opening, or spandrel, as we'll call it. And we'll take this into the RF concrete members module later. Now, something else to notice about result beams, you don't necessarily have to define it as a concrete member. It could be timber, it could be a steel rod. It doesn't matter because remember, we're not adding any stiffness. But the reason why I've set it to a rectangular concrete material for this particular case is because I do want to take it into the RF concrete members to design it later on, which does require concrete shapes and materials. Okay, so now that we have covered the basics of the surface and beam members, I want to talk about the eye cracked. Now the eye cracked is just simply the gross moment of inertia multiplied by a factor, and this comes directly from table 66311A within the ACI. The ACI requires us to take into consideration crack section properties. Now this factor multiplied by the gross moment of inertia varies for each element, whether it's a column or a beam or a surface. So by default, the program will automatically use the gross moment of inertia. So how do we go ahead and change that? Well, you can see here I can highlight both of my columns at the same time, and I can double click them to edit them. Here we have a Modify Stiffness tab. Within this drop-down box, you'll see here both the ACI and the CSA because the concept is the same for both standards. Well, within the ACI, I can use my drop-down box here to select columns. And now this multiplication factor, which comes directly from table 6 within the ACI, will be applied to my flexural stiffness. So that's how we account for eye cracked. Now, the same thing needs to be done for our rib elements. I can highlight both of them, choose my Modify Stiffness tab according to beams here, and the program's smart enough to recognize what type of element is from this drop-down. We also would like to do our elevated slabs here. So holding down my Control key, I select all of the horizontal slab elements, edit the surface, and even for surfaces, we also have a Modify Stiffness tab according to the ACI for flat plates and flat slabs. We click OK, and last but not least, we have our wall elements. So I can graphically choose these with my selection box. I right-click to edit these surfaces. And again, under the Modify Stiffness tab, the program gives me the option for walls uncracked or walls cracked. We'll go ahead with walls uncracked for this example today. Now, you'll notice that I did not apply an eye cracked consideration to my result beam. Well, the reason why is because, remember, we're just creating a summary of the forces and stresses within this wall panel. I've already considered eye cracked for the wall. So there would be no reason to also do it for a beam type element. With that said, if you even take a look at the result beam, we don't have a Modify Stiffness tab anyway to make that change. Okay, one more concept to take a look at before we look at the loading, and that is our Fe Mesh. Under Calculate Fe Mesh Settings, the global Fe Mesh by default is set to 1 foot. So you can adjust this as necessary, but taking a look at the 1 foot mesh setting, for example, today we can regenerate the Fe Mesh. And maybe I turn this into wireframe view. Well, you can see that the program automatically meshes everything for us. So nodes, members, openings, everything is automatically meshed and tied together, so we don't have to take care of any of that manually. Now, also keep in mind that you don't need to even mesh the model before you run an analysis. This will automatically always be done. I just wanted to give you an idea of what was going on in the background. Okay, and lastly, let's look at the different loads that I've placed on this structure. So I have applied different loads according to dead load, live load, snow load, and so on. When we look at the loads applied to the structure, they're just simple surface loads. So for dead load, you can see those acting in the vertical direction on all elevated slabs. Same concept for live load, but only applied at our second level inside the building. Snow load, I've accounted for some high drifts here closest to the wall surface bases. So maybe we're wanting to take into consideration the analysis for high snow loads. You can see those applied here. Lastly, we have our wind loads. We can see an external pressure being applied in the global X direction, as well as some wind loads, again, all surface loads applied on the inside of our structure as well for an outward pressure. Same concept for wind in the Y direction, except where we're just rotating the directions here 90 degrees. So we have a wind in the global Y direction with the surface loads applied. Now, jumping to the load combinations, I can open up my load combinations tab. We can see here the program has automatically generated all of my LRFD load combinations denoted by this orange color. The program has also created my ASD load combinations. Now, both of these combinations are going to be used later on for design within the concrete modules. But if we want to jump back to RFEM, well, here are all of these same load combinations available in my dropdown, and I can actually see the loads being applied stacked on top of each other, one by one within these load combinations. The load factors are also considered here graphically. So now we're finally ready to run our analysis. So what I can do is just go to calculate, calculate all. And what the program's going to do is cycle through, first of all, my load cases and then all of my load combinations. Keep in mind, for load combinations, the default is a nonlinear analysis, taking into account secondary effects such as P delta. So for every iteration, our stiffness matrix is being adjusted to account for those P delta effects. We're also taking into account those stiffness modifications from I cracked. So once the analysis is done running, we will be presented here with our results directly in RFEM. Now, the results are available here under the Results tab within the Project Navigator, and we can quickly take a look at our deformations. So turning this into wireframe view, we can cycle through these different load combinations up here in our toolbar, and for the most part, it looks like gravity loads are affecting the structure. Now, deformations aside, we're most likely for concrete design very interested in internal forces, especially for our members. So what we can do here is jump to the members tree within our Project Navigator to go ahead and display the internal forces. So for example, I'm looking at the axial loads within my column and my rib members. We can also take a look at shear loads. Maybe we're interested in that for those rib members. Bending moments, of course, we want to use for our tension reinforcement design, and so on. Now, we can always right-click on one of these members to go to the results diagram. The results diagram allows us to turn on these internal forces and to see a little bit more detailed look at what's going on along the member length. We can also quickly cycle through different load combinations to see how those forces are changing. The other thing I want to point out is remember our result beam up here. So let me create a visibility by my selected object here of just my result beam. Well, remember that this is integrating the stresses from my wall element and presenting it to me in a beam type format. So this is actually the area above my wall opening. I can view normal forces, I can view the shear forces, even the bending forces all along that wall segment. So again, this is what we could take not only for the result beam, but for all beams into our own design tools to take a look at the reinforcement design with these internal forces. Now, the same can be said for support reactions, and let me make this a little bit more clear here. Our support reactions are given to us within this results toolbar, and we can take this into our own design tools to do the foundation design if we'd like. So that really summarizes our analysis. Again, I haven't touched any of the add-on modules. This has all been done in RFEM alone, which provides us with a full analysis. So now we want to change topics and jump to reinforcement design utilizing these add-on modules within RFEM. So going back to my data tab, well, we can see here the long list of add-on modules available. So this is why we have the concept kind of pay for what you use, because not all people are going to utilize all these add-on modules. Well, we can always right-click and move a module up to the top of the list by selecting it as our favorite. Also, under the add-on modules option up here at the top of the screen, they're categorized a little bit better so we can see design by concrete and launch the RF concrete members module. Now, when I say add-on module, nothing more than a dialog box available within RFEM itself. All of my loads, my load combinations, my cross sections, my materials are all brought in from RFEM, the main program, into this add-on module. The only thing that we need to define here is a little bit more information about our reinforcement specific to the ACI standard so that the program can go ahead and design that for us. The first thing to note here is we want to choose the standard. So you'll see in this drop-down box we have both the ACI and the CSA standard as well as Eurocode and a couple others. We'll choose ACI for today. Now the strength limit state, we will be choosing all of our LRFD load combinations, so I can move all of those over here to selected for design. Serviceability will be my ASD load combinations. Again, we can choose all of them and move them over here to selected for design. Now down at the bottom of the serviceability limit state, well, this is where we have the option to activate RF concrete nonlinear. So we won't be doing that today, but just keep that in mind that that is an option if you have that module extension to utilize the crack cross-section properties within the analysis. Now we just simply need to move down our list here from top to bottom. So moving on to materials, concrete 4000 PSI is brought in from RFEM. Our reinforcing steel is set to grade 60. Material properties are all given to us here, not too much to change. The cross sections, same concept. These are my cross sections directly from the RFEM model. Now I know it's a little bit difficult for you guys to see, but as I click through these different cross sections, they are being highlighted in the RFEM model behind me so I can see exactly which cross sections are located at which parts of the model. The ribs tab is those rib members that we created with the effective width. So remember, I define an effective width of 3 feet only on one side of my rib member. So that's all brought in from RFEM. Now this is important because we can do the reinforcement design of this effective width section here. The supports tab, this is utilized by, first of all, graphically selecting here a couple nodes. So I'm going to choose both the nodes at either end of this rib beam here in the front of my structure. And the reason for that is that I want to define my support width, which in this case are my two columns. So my columns are 12 inches wide, so we can type in here 12 inches for the support width. Is the column a direct support? And what's nice is that this picture updates to kind of let you understand what exactly you're selecting here. So is the column underneath the rib or is the rib framing into the face of the column? In our case, we'll assume that the rib is framing into the side of the column. Is it a monolithic connection? Yes or no? And is it an end support? Well, in both of our cases, we'll choose this as an end support. So what the intent of this table allows us to do is to reduce the shear forces in the support area according to the ACI 9432. The code tells us that we can actually consider the rib element at the face of the column, even more so a distance of D away from that face, D being the depth of the rib. So the shear forces at that location will be used for the shear reinforcement design. So the ACI allows us to do that. So in order to not over design the shear reinforcement, we can activate that option here. And finally, the reinforcement table, which is a bulk of our work within this add-on module. So what we want to do here is to give it the reinforcement that we'd like to use for each one of these members. So the first thing to do is to create a reinforcement group, and we'll start here with our columns. So we give it the description. Now for my columns, I don't want this to apply to all my members, but rather I'm going to clear this out and only select my two column members at the front of my structure. So from here, looking at the longitudinal reinforcement, I'm only going to select the rebar sizes that I'm interested in having the program optimize for my longitudinal reinforcement. So let's say I want the program to choose between number 5s and number 6s. The max number of layers, well, currently this is set at 1 layer, but there are situations, especially for beam members, where we want 2 or more layers, depending on how deep that beam is. So that's possible to set here. The anchorage type is our development length. So do we prefer this to be straight, to be hook, to be a bend? Well, the program will go ahead and give you all of the dimensions for that based on the ACI standards as well as our applied internal forces. The curtailment type, well, what this allows us to do is to specify different areas within the member length that might need additional longitudinal reinforcement. So a good example of this might be our rib member. Well, our rib member is going to have significant bending at the center, but we're going to have much less bending at the end. So what you can do is to set different curtailment so that the program can optimize where to put that longitudinal reinforcement in different zones. Now, the option for no curtailment, that will use the same longitudinal reinforcement throughout the entire length of the beam. Ties and stirrups, same concept. We just want to choose the possible bars here. For these columns, I'm going to choose number 3s. And we're going to use uniform spacing throughout, which is the default option here. Now, the program can also take into consideration the max stirrup spacing according to the ACI standard. So it will either flag us or design it to make sure we're not exceeding that particular code check within the ACI. The reinforcement layout. The first thing to set here is the concrete cover. The ACI standard refers to table 26131 for concrete designation, and for number 5s or smaller that are exposed to weather, the code tells us that 1.5 inches is adequate. So assuming we're using number 5s here, we'll just keep this as the default of 1.5 inches. If the program came up with number 6s for my reinforcement, well, maybe I'd want to go back and adjust this to something more like 2 inches. The reinforcement layout. Well, remember, we're designing our columns here. So a reinforcement layout shown in this picture on the right is not ideal for a column. We're going to have something more like biaxial bending. We could bend about either axis. So we want to certainly make sure that we have bending reinforcement on every face. So for that, we can use this drop-down box to choose the option uniformly surrounding. So this looks much more efficient and effective for a column member. The relevant internal forces for concrete design, we will design for axial loads, shear loads, bending loads, and torsion. If by chance you're not interested in designing the reinforcement for one of these internal forces, maybe torsion is not a concern for our columns. Well, you can always use this option to uncheck any of these internal forces then, so they will not be considered within the design. The minimum reinforcement, the thing to know about here is these checkboxes are efficient. Essentially, this is going to refer back to the ACI standard and use the minimum longitudinal or shear reinforcement that's required by the standard. So the program will at least put in this much reinforcement when it comes to both the longitudinal and shear, and by all means, you can also put in your own minimum reinforcement by typing it in manually. The ACI tab, just a little bit more information relevant to the ACI standard alone. For example, the max percentage of reinforcement is set at 8%. This comes from the ACI section 10611 for columns. The ACI states that we should have no more than 8% of steel to concrete ratio. So you may adjust this for other settings, but for now we'll refer to the ACI standard. Same thing for shear and torsion reinforcement, just some settings here according to the ACI Chapter 22. These strength reduction factors for concrete design, we're all familiar with this, just referencing Chapter 21. These are automatically set to default from the ACI standard, but you can adjust those if you see fit. Now, lastly, we have our Serviceability tab. So keep in mind, this Serviceability tab is only available because back under the General Data tab and the Serviceability limits, I've actually utilized my ASD load combinations. If I did not have load combinations over on this right side of this dialog box, then I would not see this Serviceability tab. But today we are designing serviceability according to the ASD load combination. So there are two considerations when it comes to serviceability. We have cracking and deflection. So with cracking, the first thing to specify is the limit value for allowable crack width. Well, utilizing this first option, limit values, my drop-down box has a few default options, and this just comes from the ACI committee, did some research, put together the recommendations depending on where your structure is located and how it's going to be used. So for example, water retaining structures are going to have a significantly lower allowable crack width of 0.004 inches in comparison to a structure with a protective membrane or that's located in a dry air environment. Well, for today, let's assume that cracking is not such a concern for this structure. We're in a very dry environment. We don't expect it to see very much cracking. Anyway, so we'll just set the limit values as 0.016. Now, user defined, you can manually type in the allowable crack width as well. So below this are two different checkboxes, design without direct crack width calculation according to Chapter 24. Well, the ACI does not specifically give us any type of equation or references when it comes to the actual crack width. Instead, it tells us that we must limit the reinforcement spacing in order to control cracking. So by leaving this checkbox checked, we will check the spacing of the reinforcement to make sure we're adhering to the ACI standard. The second option, design with direct crack width calculation, this will refer to the Gurgley-Lutz equation. It's a much more theoretical approach where we will calculate the crack width and compare it to this limiting value up here. So in this case, we will leave both of these checked. For deflection analysis, you'll notice that when I check this on, I now have an additional table here called deflection data. I can activate long-term deflection according to Chapter 24. I just input my duration of my load in months, and the program will find the applicable factor from the ACI standard to apply to our deflection. Under the deflection data, not much to do here because the program already recognizes that we need to add both columns to this table, member 1 and member 2. The reference length is set as the distance between the supports, the full 10 feet. You can also modify this here with these drop-down options. If we did have a pre-camber in here, we could put that in. And finally, the limiting values. The drop-down box has a few options directly from the ACI standard, or you can type in your own user-defined as well. Utilizing L over 240 again from the ACI, well, now I'm telling the program that I cannot exceed a deflection of 0.48 inches. So it will compare the demand deflections from our analysis to these limiting deflections and give us a capacity ratio for serviceability. So as I mentioned, that was a bulk majority of our input information within this module. Now keep in mind, this is only for the columns. So what I'd also like to do is design my ribs and my result beam at the same time. Well, we can do all of this in one continuous step by simply creating a copy of my reinforcement group. So now my columns are defined here twice. All I need to go to is a second group, and we'll rename this to ribs. Now the members, I need to graphically choose my rib members that I'd like to apply this to. And as far as the rest of these tabs, most of this will remain unchanged. So for example, the longitudinal reinforcement will still let the program optimize between number 5s or number 6s. The ties, maybe I'd like to increase this to number 4s. I expect to see higher shear here, of course, in comparison to my column, so we'll increase this to number 4s. And let's use different zones. So therefore, the program will optimize in 3 different zones the spacing. Areas where we have higher shear will have closer tie spacing. Area where we have lower shear, of course, will have further away tie spacing. The reinforcement layout, the cover is fine, but the reinforcement layout, well, this is not correct. We certainly don't have a column situation where we need uniformly surrounding reinforcement. So instead, we're going to choose symmetrical distribution. So you'll notice now we're giving reinforcement at the top and at the bottom, which is more beam-like behavior. For rib elements, we now have the option to distribute the reinforcement over the complete slab width. So we're also going to extend this longitudinal reinforcement over the effective width of our slab. So pretty powerful in the sense that we can design these rib elements directly within this module too, and taking into account that effective width that we input in the RFEM model. Now, as for the rest of these tabs, essentially we can leave everything the same. Even for serviceability, if I go to my deflection data table, members number 3 and 4 were added. My allowable deflection will now be around 1.5 to 1.7 for these rib members simply because they are longer members. Okay, and finally, we have our result beam up here. Now remember, we're just designing the upper portion of this wall above the opening as a spandrel, and we do so by, I guess, mimicking that it's a beam type element. So creating a copy now of my rib reinforcement group, and you can see here now I have columns, ribs, and my third option, we can rename this to spandrel. Well, here I can select my member, my result beam graphically within the RFEM model. And jumping back to my longitudinal reinforcement, this looks fine. My ties and stirrups, maybe we'll jump back to number 3s here with uniform spacing. Everything else remains unchanged. Even the reinforcement layout, by the way, this will look the same as our rib members, but our cross section was updated here, top and bottom reinforcement. The only thing that maybe I'm not so concerned about is my serviceability with deflection consideration. So you can uncheck these options for different reinforcement groups. So I still want to check out my cracking, but I don't really care much about my deflection. So I can simply uncheck that, and now that member will not be included in the deflection data table here. So now we have finally defined all of our reinforcement settings for our members, and we can run a calculation. Now all this is doing is pulling the internal forces from RFEM into this add-on module, applying the ACI equations to give us our actual reinforcement details for each member. And you can see it solves fairly quickly. So now we're presented here with our results in table format. The required reinforcement is given first here, and we can check it out by member. Now again, these tables are synced up in the background with the RFEM model, so we can see exactly where we're at within this structure. And taking a look at our rib members in particular, we will see the required reinforcement based on the applied loads for the AS top is given as such. Now AS bottom, this is all longitudinal reinforcement. We're also given our requirements for shear reinforcement and torsion. So required reinforcement is nice, this is good to know, but rather we're probably interested in, well, what rebars did the program lay out for these particular members in regards to the settings that we previously defined? Well, this is where the provided reinforcement tables can be useful. Here we can see these same members defined. So for example, we're taking a look at the longitudinal reinforcement for my columns. I can take a look at my rib members here, and we can zoom in to see the longitudinal reinforcement applied at the bottom, at the top. Shear reinforcement, same concept. We can see our ties, our stirrups placed along the member length, 31 number 3s at 4 inches on center. Now, for these 3D drawings, you can always double click on it, and up pops a nice rendering here of exactly what our reinforcement looks like for both the longitudinal and the ties. If you want to make quick changes, so for example, I really would prefer to use number 4s rather than number 3s, I've decided, well, I don't necessarily have to go back to my original input data. I just simply call out or double click on this call out here, and I can change the bar number to number 4s, and maybe I increase my spacing to 0.42, 5 inches on center. I click OK, the program automatically updates the picture. I can exit out of this picture, and when I click into another table, the program says, wait a minute, you made a change. I need to quickly recalculate this to make sure you're still meeting all the ACI limitations. So I've made that change to my shear reinforcement for my column. It's reflected here with 24 number 4s, but I am getting a note now, which I can read this either under my messages or down here in the lower dialog box, it says the bar spacing is greater than the maximum spacing. So that's telling me that something is not adhered by the ACI standard. So maybe I need to go back to my number 3s or to decrease my settings there. Now, lastly, we have our serviceability check. Remember, we were checking deflections. We were also checking the spacing of our reinforcement and the crack width. So ultimately, for our different cross sections and members, we're getting a capacity here for serviceability. It looks like in this case, the deflection is controlling at the mid-span, denoted by this big red arrow for our rib member, and we get a serviceability check of 0.94, but we're still less than 1.0, so we get our nice green smiley face here. So the tables are nice, but it's also beneficial to see what's graphically going on within our module or within RFEM. So what we can do is to click on the graphics button down at the bottom, and now we are back within RFEM, but we're still technically in this add-on module. You can see that we're in RF Concrete members. So this is all my reinforcement results details from the module. Now, focusing in on a rib member, for example, we'll highlight it, we'll create a visibility by selected objects. Let's turn this into wireframe view and zoom in here a little bit. So for this rib member, what we can do is display here a diagram of our required reinforcement at the bottom of this member. So this member is in positive bending moment. We need reinforcement on the bottom, obviously, up to 2.06 inches squared per foot. So that's just the required reinforcement. Well, I can overlay on top of this the provided reinforcement. So this is what the program has determined to put into this beam member with our number 5s, and it comes out to 3.88 inches squared per foot. So you can see here that the provided reinforcement should always be greater than the required reinforcement. Otherwise, we should be a little bit concerned with our concrete design not meeting the minimums. Now you can go ahead and display all these different diagrams. What's also beneficial is we can display the rendering of the reinforcement for both the ties and the longitudinal reinforcement directly within the model. So we can see here, even with these rib members, we're able to see the longitudinal reinforcement within the slab. Shear spacing, our 3 different shear spacing zones are displayed here. Now any of this can be added to our printout report for just recommendations on how the overall rebar reinforcement design will be done. Okay, so the other thing to quickly point out, of course, is remember our result beam. We're going to cancel out this visibility mode, and maybe we highlight our result beam here along with our wall panel, create a visibility by the selected object. So here we can actually see the reinforcement above that wall opening. It was designed like a beam member. So we have our longitudinal reinforcement shown here. We have our stirrup shown, and this is all meeting the design demands of this wall panel above the opening. So again, this is how result beams can be utilized along with surfaces. Okay, so now we have completed the member design. We're also interested in the surface design. So for this, I'm going to cancel out my visibility mode, and we'll turn to the normal view here of RFEM, and we'll jump to RF Concrete Surfaces. So this is our second add-on module today. Now this add-on module is truly almost identical to RF Concrete members. Once you grasp the handle of one module, you'll certainly understand what's going on in the other. We're going to choose the ACI standard from our drop-down box here. The strength limit state design, we will choose our LRFD load combinations, and serviceability, we will choose our ASD load combinations. Under the serviceability limit state, well, this is where we can, number 1, go into these edit settings and activate the RF Concrete Deflect module. So this is the module extension that allows us to check deflection considerations for our 2D surfaces. Now you can also activate long-term deflection or turn it off here, and the design of cracks will also be included. We also can get into nonlinear analysis with the module extension RF Concrete Nonlinear, which we won't be doing today, but this is where you also activate it for the serviceability limit state design. So again, just moving from top to bottom with our tables here. Our materials, 4,000 PSI, grade 60 reinforcing steel, everything looks great there. The surfaces. So this table is really effective for our serviceability design. This has information on our deformation and crack widths according to the surfaces. So the first tab here, deformation analysis, is only available because I have activated RF Concrete Deflect. Here we type in our limiting deflection ratio. You can see the default is set at L over 250, so I can manually change this deflection ratio here as well. As far as L, this will be measured by the minimum boundary line, the maximum boundary line, maybe a user-defined value, or what I'm going to do in this case is I'm going to tell the program I don't want any deflections of my slabs or my surfaces to exceed 1.0 in this case. So that's the absolute deflection here. Now you individually can set deflection ratios for each surface, or you can apply them all at one time. The limit of crack widths, this should look very familiar. This is exactly what we just saw with the RF Concrete Members module. We can set our limiting values here according to the ACI committee for a dry air structure of 0.016 inches. We can design the reinforcement with spacing considerations according to Chapter 24, as well as run the Gurley-Lutz equation to give us our actual crack width and compare it to the limiting value set here. So nothing different here. Moving on to reinforcement. So the first thing we want to do is to again define our reinforcement group. We're only going to have time to do our walls today, but keep in mind the design of the elevated slabs is identical to what I'm about to show you. You just can create a second reinforcement group if you'd like. So this is not going to apply to all surfaces, but rather I'm just going to design these two outer perimeter shear walls here. So we can select them graphically, surfaces 15 and 16, and I click OK. The reinforcement ratios, well, there are some default settings here. For example, maximum reinforcement percentage is set at 9%. Well, the ACI standard actually tells you that for surface reinforcement, we're actually more concerned with the strain being less than 0.004 rather than a specific percentage called out. But you can adjust this percentage as a user in order to make sure that we have a strain that's below what the standard tells us to. The reinforcement layout, this is to specify the cover. Well, I'm going to specify the cover from the edge of the slab or the edge of the surface to the edge of the rebar. And for this, just like my concrete members, I'm going to set this all as 1.5 inches. We will design both transverse and longitudinal reinforcement for surfaces. What is nice is if you have any type of specialty structure that maybe you don't have a complete 90-degree angle between those two directions, you can actually adjust this angle to something else. So it doesn't necessarily have to be 90 degrees. Longitudinal reinforcement. For my wall elements, I know that I want to come in here and I'm going to apply number 5s at 12 inches on center. That is my provided basic reinforcement I'm going to put in here. So I can go ahead and input that information here for the top and bottom as well as the diameter of my rebar, but we can also utilize this helpful tool here. So with this tool, I can choose all options for top, bottom, and in both directions. I can specify my number 5 rebar diameter, which is 0.625 inches, and I can set my rebar spacing as 12. Once I click OK, the program will automatically calculate my reinforcement area and set my diameter according to those settings here. So nothing to do further with my number 5s at 12 inches. Now, these next two settings are interesting. So the program is going to first run through the ultimate or the strength limit state design. If it determines that my number 5s at 12 inches are not adequate, it will automatically increase this reinforcement. So this will be our new required additional reinforcement. So once the strength limit state design is done and we move on to serviceability, what do you want the program to use? Do you want the program just to use our number 5s at 12? Do you want it to use the required additional reinforcement? And all of those options are available within this drop-down box here. So I'm telling the program, okay, if number 5s at 12s are not adequate, let's go ahead and use whatever the program's suggesting that I need to additionally add to these wall segments. Same thing with the check of the shear resistance. Apply the greater value from either the required or provided reinforcement. The Aci tab, this just has some references directly to the standards. So for example, we want to have the minimum longitudinal reinforcement for walls according to Chapter 11. Minimum shear reinforcement is given here, as well as the nominal shear strength of our concrete according to Chapter 22. And again, strength reduction factors from 21 are given by default directly from the ACI, but you can adjust those here. The design method will leave this as the default. We have optimization of design internal forces, and the parentheses really gives you the information that you need. This is recommended for parts loaded mostly by bending or tension. This is in comparison to parts loaded by pressure, so we'll go ahead and leave this option here. So now we're finally ready to run our calculation. Now, for the sake of time, I'm going to jump to an already solved model here, and the reason why is we do have several FE elements now, which is much different than our members. So it just takes a minute to solve, and for the sake of time, we'll jump to the results, which are provided to us within this add-on module with the results tables. So the first thing I want to look at are my required reinforcement by surfaces. So once I run my calculation, I see my 2 surfaces listed here. The first one is surface number 14. That's on this far side back here. Well, surface number 14 shows me my required reinforcement within this column. Okay, so this is just what's required based on the applied forces. No problem. Basic reinforcement is my number 5s at 12 inches. This is what I told the program to input in for the basic reinforcement. My third column is all zeros. The reason why is because my number 5s at 12 inches are completely adequate for this particular wall. So I don't need any additional reinforcement. My number 5s at 12s are fine. I could maybe even consider increasing the spacing or decreasing the bar size to be a little bit more competitive here. Now, looking at wall segment number 15, it is a very different story here. Looking at the required reinforcement, I have values clear up to 0.95 inches squared per foot. That's a whole lot of reinforcement. So my number 5s at 12 inches listed in my second column here are not even going to be close to this. So in my third column, the program's telling me you need to put quite a bit more reinforcement into this wall. Then if I take a look at my shear reinforcement design, the program's giving me a not designable message. It says down here in the bottom, the shear resistance cannot be checked. The cross section is entirely cracked. Well, this raises a red flag to me. These 2 wall panels are very similar. Why is wall number 14 passing with flying colors? Everything is totally content with the number 5s at 12 inches, but then when I look at number 15, it's not even close. It's failing by quite a bit. So this tells me that I need to maybe take a look at my graphics within the RFEM model here to see what's going on. Well, remember, I'm still in this add-on module, RF Concrete Surfaces. I'm just viewing my results graphically here back in RFEM. So we'll take a look at our required reinforcement, which I can choose within my tree here. And now I'm viewing the required reinforcement for both the top and bottom and in both directions. And we can see the direction indicated by the red arrows there. Well, you'll notice as I cycle through these, the wall panels themselves, for the most part, require very little reinforcement, but we definitely have a problem up here in this corner. Very, very high reinforcement is required. So this tells me that we have an issue called a singularity. Now, if we look at this corner here of this wall panel, we have this additional wall panel framing in from 90 degrees. Remember, we have our rib member framing in all to this teeny tiny Fe mesh point in the corner. Well, in reality, this is not just an issue within RFEM, but with all finite element analysis software, that the load isn't going to be distributed at this one single little mesh point, but rather we're going to have better load distribution in real life. So what can we do in our model to take care of these high peak areas? Well, the first thing to know is that my Fe mesh elements here are pretty large at 1 foot. So maybe I want to refine my Fe mesh at this corner point. Well, I can do this by right-clicking on the node. I can edit or create a new Fe Mesh Refinement. I choose the definition type here, and you'll notice the program already chooses the node option because that's what I've highlighted in the model. I'm going to give the Fe Mesh Refinement a radius of 3 feet. Now, on the inner side of this Fe Mesh Refinement, I want 1 inch. And then as the outer mesh refinement, I would like it to transition back to my global settings of 1 foot. And I click OK. Program tells me it needs to clear the results. So now we're presented with this Fe Mesh Refinement symbol here. I can go to Calculate, Generate Fe Mesh, and maybe if I hide my objects in the background, we zoom in here, we can see that the Fe Mesh is much smaller at this corner now. Then it transitions nicely back into that 1 foot setting. So some nice automated features here. But because we've completely changed the Fe Mesh, the program does need to rerun the analysis way back in RFEM. Our internal forces are inevitably going to change when we make changes to our Fe Mesh. So I'm going to go to Calculate, Calculate All, and again, for the sake of time, we'll just jump to an already saved model here. So now I'm presented with my results after I place this Fe Mesh Refinement in RFEM. So we're back to viewing the forces within this wall segment. And I'm looking at the shear in the local X direction, for example. Well, I can see now that I just have this tiny little Fe Mesh element that has really high forces. The same thing can be said for all of these internal forces that can be displayed. This corner is certainly a problem, but at least we've narrowed it down to a much smaller Fe mesh point here rather than the entire 1 foot by 1 foot corner. So we've refined the Fe mesh, but how do we get better distribution over these high peak areas? Well, under the Data tab, we have a nice feature called Average Region. So if I right-click on Average Region to create a new average region, what this allows me to do is to, number 1, specify which surface I want to apply this average region to. And I can click on the wall panel itself, surface number 15. I want a circular average region, so the picture updates nicely here. I choose where to place this average region, which you can see we'll place it right here in the corner, and the nodes are automatically entered with the correct coordinates into this dialog box. The dimension will be 3 feet, so 1.5 radius is what we'll consider. And the program is going to automatically average out the results within this average region. So I can click OK. Now I don't even have to rerun my analysis. The program can automatically average out those regions. So now when I go back to my shear reinforcement, or sorry, my internal forces for my shear, without the average region, we have a shear force of 16 kips per feet. Now I can activate this average region at the very bottom of my results panel here. My shear went from 16 kips per foot to 0.44. So that is a significant drop. So average regions can be incredibly useful for regions where we're dealing with singularities. Now the same goes for any one of these internal forces. So now we've taken into consideration better load distribution, or averaging out those high peak areas. So we've done that for RFEM, but keep in mind that under the RF Concrete Surfaces module, The program will still automatically use those high peak areas unless we go under the Details tab and we choose this option here to apply the average internal forces for ULS and SLS calculation. So now the program will use those average out internal forces to do our reinforcement design, and we're ready to rerun our calculation. So I already have the results saved here within the RF Concrete Surfaces module, taking into consideration the average region, and now we can see much more realistic results for my second wall panel here. For surface number 15, here is my required reinforcement. We're no longer seeing 0.95 inches, but the greatest area that we're seeing is 0.3 inches squared per foot. Well, now my number 5s at 12 inches are completely adequate. I don't even need any additional reinforcement here. Even my shear reinforcement, I don't need any shear reinforcement. What I provided in the program is adequate. I don't have any non-designable errors telling me the entire cross-section is cracked. Now, lastly, we can view this information graphically again, and we can take a look at the required reinforcement in the different directions. Now, by all means, we still have these areas which have higher internal forces, which is fine. This probably stems from our rib and our panels framing into it behind this particular wall. But we're not looking at 0.95 inches squared per foot. Again, we're looking at the max of 0.3 inches squared per foot. So that is much more realistic. Okay, so that really summarizes, I know rather quickly, member and surface design within RFEM. So at last, we can jump to the PowerPoint to go ahead and conclude today's webinar. I do know that that was an incredible amount of information. You can always visit our website at dlubal.com to read more about RFEM as well as these concrete design modules. I always want to encourage everyone to check out our social media sites. For example, our YouTube channel has additional recorded webinars similar to this one that you can watch on demand. Also, things like events and conferences you'll find on these sites, knowledge-based articles with tips and tricks and technical articles are available. If you do have any questions regarding the webinar today or any other questions, feel free to either email us or call our office located in Philadelphia. The email is info-us@dlubal.com. And again, our phone number here in our Philadelphia office is 267-702-2815. We will have many more upcoming webinars. I try and do one once every month or every 2 months. You can register under dlubal.com support and learning webinars. As most of you know today, though, I sent out a couple reminder emails when these webinars will be available. As far as Pdh credit, many of you have attended today's session and are hoping to get Pdh credit. That's great. I'm happy to issue you that certificate. Just a couple of requests. Number one is that you were here for the full 60 minutes. And number two, if you can send that request to our email at info-us@dlubal.com. Again, info-us@dlubal.com. Just let me know who is in attendance today, and I will gladly issue that certificate back to you. And with that said, I want to thank everyone for attending today's webinar, and as always, we hope to see you at the next one. Thank you.